And thanks a lot for inviting me to give this lecture on a subject that is something I've been studying for almost 40 years. I mean, longer because it's also in high school, but I've been studying as a research project almost 40 years. And I gave a similar lecture at the Easter Summer School a few years ago. So there's some new elements, but it is similar to those of you who were there. I apologize if it's a repeat, but it's really exciting, I think, as a subject. Maybe not the word I said, but the subject I find really interesting. So it's about the structure of complex atoms. Any atom which is not hydrogen, I will call complex. So it's about basically all that. So here's what I'd like to talk about. Well, I'll discuss a little bit the periodic table of the elements. So start with what we know historically. Then I will look at certain properties of atoms to focus on just a few. So ionization and radius is something I will discuss, a particular subject. And for the ionization energy and the radius, but also how many electrons. So when I talk about ionization energy, I will talk about the energy it costs to remove electrons from an atom. But we will also talk about how negatively we can ionize an atom. I mean, how many electrons can an atom find beyond neutrality? And in particular, I want to discuss the way the periodic table is built. Some of you may have, I mean, you all know the periodic table, I'm sure. Whether you know what's called the Aufbau principle, the way that it's actually structured, that's usually maybe not taught in high school. So I'll discuss it and a particular nice representation of it. And then I'll start coming to the mathematics. I will discuss different models of atoms. And the basic model I want to discuss is the quantum description of the atom, the full quantum description, but non-relativistically. So one could discuss relativistic corrections as well, but I'm not going to do it here. When I allow myself to look at the many-body quantum description of the atom in a non-relativistic setting, then there's no limit to how large an atom can be. Right? I mean, the atomic number could be 5 million. The reason we don't see them in real life, I mean, the Z in the atomic number could be 5 million. I mean, the model describes such an atom. That would certainly be complex. Now, the reason we don't see them is really twofold. One is that the nucleus becomes unstable, and that happens already around 1992. There are some unstable even before that, but around 92 they become unstable. But more importantly, it also becomes unstable because of relativistic correction. Now, it's believed that the nuclei, that there actually is a stable island of nuclei when we get to even bigger nuclei than the ones we've seen, so around 124 or 125, then maybe there could again be stable nuclei. And we could maybe see such atoms. I mean, when I say stable, I mean that they have a lifetime, which is long enough that one can study the atom. They're not really stable to exist for a very long time. But as you get to 137, which is 1 over the fine structure constant, and I don't need more than just a few, just 1 over 137. When Z is 137, 1 divided by the fine structure constant, then atoms become unstable because of relativistic correction. The electrons simply fall into. But I will study non-relativistic. So that's the model I'll start with. That's the most complicated. And I'll start bounding the energy and defining what I mean by the ionization, the radius. I'll give the mathematical definition. And I will give the first simple bounds on the energy, simple bounds on the maximal ionization, bounds due to Lieb, and I'll formulate the ionization conjecture. So that's my hope to do this in this lecture. I may not get there, but of course I have 5 lectures, so I'll just push it to the next lecture. And this is really lecture 2 for this afternoon. So I'll get to that later. If we exit it slowly. Okay, I'll use the. Oops, now it reacted, so I go back. So that's the periodic table the way you're used to see. And that's Mendeleev, who was the first one, or at least credited to having discovered that there was a periodicity in connecting the size, the mass of the elements with their chemical properties, right? So this is from his original paper, and this is how we learn the periodic table today. Now, the point is that as you go down the groups, so the columns in the periodic table I will call groups, the rows are just called rows, but the groups correspond to elements that have more or less the same property. Right? So the elements out there, these are called the noble gases, and that's because they have a filled shell at the end, so they don't have very strong chemical interest. But in general, we'll try to see, is it really true that as you go down these different groups, that you have similar chemical properties? So one should be able to understand this mathematically if it is true. Now the group over here is the one where you have added one electron to the noble gas. So these are called the alkali atoms. They have an extra electron running around a core with filled gas. Right? And that, of course, has something to do with their chemical properties. Now, this is not really the best way of writing the periodic table, and I'll get to that in a moment. But let me just start with the two properties that I'm interested in. And I'm just picking two, right? Because I know how to study those mathematically. So that's the ionization energy and the radius of it. Both are big. The ionization energy is not so difficult to define. The atomic radius is actually also not very difficult to define, but it has still, it's a question whether you can actually measure it. Can you measure the radius of the atom? Because after all, atoms, if you strictly speaking, ask, when do you not see electrons anymore? Well, then the radius is infinite, because they don't have compact support, the waveforms. So you have to decide exactly what do you mean by the radius, but also then how do you actually measure it? And what I don't know if you can read it here, but it says atomic radius, and it says empirical. So there's an empirical way to measure the radius of atoms. And it actually goes way back to Bragg from the 1920s or even earlier, where he decided to look at binding length in molecules and saying maybe atoms, when they bind, it's like you just find the bond distance by adding the radii. So there's sort of an empirical way that you can find the radius as associating a number to each atom so that the binding distance, the bond length, is the sum of the radii. And that turns out actually to be pretty accurate. I mean, Pauling was the one that promoted this idea the most. And if you go through, it seems to be actually quite consistent, that it's really the same radius that you will find in all chemical bonds that the atom. I mean, it's not perfect, it's an empirical definition. So what's shown here are the empirical radii. And you can see that it looks pretty right, that as you go in the different groups, that it's pretty much the same. What you should also notice is that the radii do not change very much across the periodic table. Right? So down here we have, somewhere here we have uranium that has 92. Uranium is the largest natural atom. It has 92 electrons. And somewhere there we have lithium that has 3 electrons, but they're pretty much the same weight. In fact, to quite high numerical accuracy, they have the same. So there is sort of a perfect balance between all the forces in the atom, that the 92 electrons in uranium take up the same space as in lithium. So this is something we would also like to understand, the universal property of the wave. So in fact, you may ask now, if we go to this infinite periodic table, I just told you that I could go to Z being 5 million. There's no limit when I only study non-relativistic atoms. And I'm going to define for you what I mean by the radius. That may not be exactly what is being measured, but for some groups, well, I'll tell you, I have a definition that depends on the parameter, and then we can study the radius of it. Now, and then we may ask, could it be that if we go down the group, so now imagine that we go to this infinitely big periodic table, and I now continue down the group to the infinite periodic table. Could it be that the radius actually converges? I mean, it looks a little bit like they get bigger and bigger and bigger, but maybe they actually will converge. So that's the point I'll try to make. It's a conjecture that I'll try to make, that the radius actually converges as you take the limit of z going to infinity through the groups in the period. Of course, we also have the periodicity, and that's why I use this representation. You should think of that as you come around here, you've come through a period. Actually, the periods get bigger and bigger, so we have to understand in what sense is the periodic table periodic, and is it periodic? And could it be that the infinite periodic table actually really does become periodic in some sense? But it does look convincing that along each of the groups, that the property, I mean, there's a big jump here from the radius there to the radius here, but it seems pretty much to be the same, or having at least a slow change if you go within a group, and maybe it converges if you have infinitely big groups. So these are the kind of questions I'll ask. The same things are for the ionization energies, right? So this is the ionization energy. I told you that the alkalis in here, they have one extra electron running around on top of the shell of the noble gas. And of course, that electron is fairly easy to remove. It costs very little energy to remove an electron from an alkali from the first group. So the ionization energies there are rather small, whereas the energy of the ionization energy for the noble gases is pretty high. It's difficult to remove an electron from this very close shell. And this is sort of reflected also. The radius of the alkali is very big because this extra electron is sitting inside of it. When I first pressed it, I had to wait. Oh well. Yes, there was not. Okay, here are some other. I'm sorry. So here are some other data. Some of it is something I collected myself. Some of it is from research papers. So let me start with this thing here. That's a little Excel sheet calculation I did myself to understand the radius in a slightly different way from looking at bond length. I asked myself, what is the number density in solid matter? Or you can recalculate it into the average interparticle distance in solid matter. Right? So you can take the solid matter of, say, sodium, and then you can ask what is so you take a cubic meter of sodium, and then you ask how many atoms are in there. Right? And then you can, from that, calculate what is the average interparticle distance. That's not a very difficult calculation to make because you know the weight of sodium, you know its weight per cubic meter. This you can also look up, and then you can write these graphs. And you see again, just as the radius, the empirical radius, if you look at the average interparticle distance in solid matter, it seems to also converge. This is group 1, group 2, and group 13. That's the noble gas that's down here. And then many years ago, I asked myself, is there a way, could I predict the radius of an atom? And I'll come to this. I studied, I cannot prove this, but I can prove something in the limit of very large atoms. But then I just extrapolated to small atoms. And then I looked at, so this graph is something I produced myself. The dotted line here is due to Bragg. As I told you, he did it in 1920. He collected the radii of atoms. And I took group 1, right, the alkalis. Later, the one from Slater determinant, we did it in 64 by looking at a larger database. When you do the empirical atom, you have to look at the database of bond length. And he had a larger database, so he did it again, and he found the dashed line. So they're not very different. The red line is actually a curve I computed theoretically. And I'm quite proud of that. I cannot prove it, but I'm still very proud how accurate that curve. This is using my definition of what the radius, my mathematical definition of what the radius is, and calculating it in a very particular model. It's the model called the Thomas Fermi model. I'll get to it. And I wrote a little paper for a chemistry journal where I somehow said that Thomas Fermi theory, which is for chemists, it's almost useless. It cannot calculate anything correctly or anything, so they forget about it. You'll hear Robert Zeiringer's talk tomorrow about density functional theories, and they're much, much more complicated theories than Thomas Fermi theory. So I wrote a little paper saying Thomas Fermi theory is much better than its reputation, and I used this to actually see it actually gets the radius pretty much correct for the alkaline. This calculation down here is done by a group that does density functional theories. So there are many, many density functional theories. These are just atomic models where you calculate energy just using the density. You'll hear more from Robert about it. These are very, very complicated models. The most famous density functional theory is the one called PBE, Perdue, Berg, and Enzerhofer. That's sort of, they almost call it the mother of all density functional theories. And Berg told me that this paper where they introduced it, they also review all density functional theories. This paper gets something like 10,000 citations a year or something like that. Or I don't know, it has hundreds of thousands of citations. That doesn't mean that his H index, I mean, his H index is 1,000,000 times higher than mine, but this one paper, of course, doesn't change the H index, but still it's pretty impressive to have a paper that gets in the thousands of citations. By the way, so the calculations I'm discussing here include PBE and also some other density functional theories. And it's actually written in a collaboration by Konstantin Snyder, Perdue, and Berg. Perdue and Berg, there's the P and the B in PBE. And somehow they were motivated at some of the questions we asked in mathematical physics, this thing of letting Z going to infinity. So, of course, chemists usually don't care because Z only goes up to 92 for them. But they were interested to test their density functional theory. Would it make sense to actually, how far could they go? So they went up to 3,000. And then they calculated the ionization energy to see if they got a limit. So they again asked this limit question. So they asked if there was a limit as you let Z go to infinity. For them, infinity was 3,000. And they found that actually there was a limit. And these are the value of the limit in the 8 main groups calculated in the different theories. So the curves here just corresponds to which curve the different curves are the different density functional theories they're using, and the numbers here is which. So one is the alkalis, again, they have very low ionization energy, and these are the noble gases that have very high ionization energy. But they found that there was convergence. But the big question is, how do you actually define the groups when Z becomes very large? So they use the formula, and I'll get to it. They use the Aufbau principle, and I'll get to it. And I actually asked them, okay, 3,000, that's fine. That's a big number. Can you do, and I was being modest. I said, can you do 50,000? And they said, yes, probably, but it would take a year for a PhD student to do it, and no chemist would care about it. Because 3,000 for them was large enough. So I have not convinced them to go to 50,000. And I would actually like them to go to 1,000,000, which is probably hopeless, but I'll explain why now. So now I come to how the periodic table is actually built. And notice that I took the original picture we had. These two, group 1 and 2, were over here. And I remember having a conversation with Jan many years ago over Zoom about the groups and so on. And Jan said, so I tried to tell him what I had learned about all these things. He said, but then it's much better to put these groups over on this side, because then the whole thing will look much better and much more structured, right? You can see here, this looks much nicer than having these two large columns over there. So I was about to sort of give full credit to Jan for this, but then discovered that this had been discovered by someone else way, way back. This person is also called Jan almost, but I think he's French, so he's called Janet. So this is called the Janet periodic table. I mean, it's the same periodic table, it's just how you structure it. And it's also sometimes called the left step periodic table. So, I mean, when I ask ChatGPT, can you show me the Janet periodic table, it corrects me and say you should call it the left step. Okay, but you see here, you actually see the structure very clearly for how the periodic table is built. So you start, so how do you, well, what do you mean build? Meaning you put in electrons, and then which group will you then be in? When are you coming back to, when is the periodicity? The colors, and maybe I didn't describe it before, but I'll do it now. The colors describe the last electron you put in, what angular momentum it is. If you remember the angular momenta are L equals 0, 1, 2, 3, and so on. And in chemistry, they call L equals 0 orbitals, they call it the S orbital. L equals 1 are called the P, and so on. So these are the S orbitals that are being filled. It doesn't mean that there are no other orbitals, but the last ones you fill, the last electron you put in is in an S. Here it's in a P, here it's in the D, and here it's in an E. So how do you build the periodic table? The first electron at all, that's in hydrogen, you put that in an S. The second one, you put in the same S because they have spin. Right? So you put two electrons, one spin up, one spin down, in an S orbit. Then you go to lithium. Now you are sort of in the second level, but you still put it in an S orbit. So you put electron, one in S, two in S, three in S, four in S, but the next one you put in it. That's the rule. And then you fill up all the P's, and then you fill the S's again. Then you do it once more. So there are always two in the same, and then you fill up. So if you tell me what is the electronic structure of this element here, I can tell you exactly how many. In here I'm filling a d orbital, so there will be 4 d electrons that are filled in, and then I go back up. I go back up here, so there were more d electrons there, right? So that will altogether be 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, and then you, I don't know why I said 14. There are 10 because there are 14 is down there. There are 10 because there are 5 in SPD. D corresponds to L equal to 2, and that has the generacy 2L plus 1, which is 2 times, what did I say? L was equal to 2, so 2 times 2 plus 1 is 5, and then we have 2 spins, so that's 10. Right, so you have 10 of these, then you have 6 of those, and so on. So you can count exactly how many electrons you have in all the orbitals. Right? And I did the calculation down here. So the formula down there is what is the Z or the Z. Let's take this one there maybe. That's the last point. This is argon, it's a noble gas. That's the last point where you're again filling in a p orbital. In the second level of p orbitals. And then I ask, what is the Z for that? So in this case, it's actually 18. And this formula describes it using the combinatorics from that. So you can go through that yourself. I'm not going to do it here. The formula is easiest if you look at the even levels. So the NL will be important for me. The NL is how many levels you have filled of angular momentum. Right? So here angular momentum, this was S. Here angular momentum is 0. So this is what I would call N0. And how many of those have I filled? Well, if I go down there, I fill 1, 2, 3, 4, 5. So this is simply which row I'm in. So the NL counts the rows I'm in the different colors. Right here I start there, so this is row 3 in the p orbitals LU. If I do the even rows, then the formula is like this. And you can just check it. That's the right formula. If I ask what is the Z, it's always when I finish filling. So it's argon, xenon, and I don't know what this is, an unknown one. And the formula is here what the Z is when I have filled 2J of those. If you did the same with hydrogen, so it's often said, oh, this is just explained by hydrogen, because in hydrogen you do the same. Well, hydrogen would not give you the same period. If you do the calculation, and I'll come to it later on, in hydrogen, if you have filled n angular momentum level, this would be the formula for Z, and that's not the same formula as there. You can just check that that's it. Okay. Now, I will be actually interested in what happens when we go to very large. Can we explain this? I mean, this cries for a mathematical explanation. If this is really true, we should be able to explain. So here I've turned it around and I have asked, if I give you the Z in these electrons here, I give you the Z, then I ask how many electrons are in angular momentum, L. And remember, you have to multiply by 2 times 2L plus 1, because in each L, the degeneracy is 2L plus 1, right? And you can put in 2 spin. So that's why I multiply 2 times 2L plus 1 times the formula there. And asymptotically, it looks like this for very large Z. If I add L to be lambda Z to the 1/3, that's just the right scaling you would do. So the Aufbau principle would tell me if I went to very, very large Z, I told you that's my motivation. I want to try to explain things in the atomic, the periodic table becomes very big. So I will let Z become very, very big. I will look at an L, which is of order lambda Z to the 1/3. That's just because that will give me the right scaling. Then the number of electrons will, at the atomic number Z, if I use this Aufbau buildup, would be this formula here. 4 lambda, some linear function, Z to the times Z to the 2. If I did the same with hydrogen, it would give me this formula. It has the same scaling, but it's a different form. It's still a linear function in lambda, but it would be a different. And I'll come back to that because I will actually prove mathematically that neither of these 2 formulas can be. They're much more complicated. Okay, so let me come now to actually the mathematics and to try to prove some of the things I've said, or to analyze them is probably the right word, in different mathematical forms. So this is the Hamiltonian of atom number Z with n electrons. I will be mostly interested in the neutral atom when n is equal to Z. But for the mathematics, Z doesn't even have to be an integer. Z is just a number, it's just a parameter. But of course, physically, Z is an integer, 1, 2, 3, and as you go through the periodic. But it didn't really happen. N is, of course, an integer, because that's the number of electrons. And if I want to have neutrality, of course, both of them would have to be an integer and would be equal. So that's the kinetic energy, minus 1/2 the Laplacian for electron I, summed over the n electrons. I am using what's called Hartree units, or atomic units, where h bar is E, is the same as the E is the charge of the electron, and M is the mass of the electron. I'm setting all of that equal. This you can do, it's just a choice of unit. And this is called Hartree units, and actually if you look up in tables, what is the ionization energy of your favorite atom, you can actually look it up in Hartree units. It's not just mathematicians inventing this unit, this is a very useful unit. For chemists also, so lots of chemistry tables are in atomic units, so that's when I'm writing it exactly. That's the electron-electron repulsion, and that's of course where all the headache is, because if we just had this, it would be a non-interacting model and it would be very easy to analyze. It's even exactly solvable, but this is where the complexity comes in. So when I talk about complex atoms, these are the atoms where this term is non-vanishing, and that's true as soon as n is bigger than 1. Right, so that's the problem. This is the kinetic energy, the attraction to the nucleus, and the electron-electron. And we have to remember that we're doing fermion, so we are in the antisymmetric subspace. So the antisymmetric product of L2 of R3 with values in C2, not to forget the spin. I mean, if I want to compare with real numbers, I should remember this. And what is then the ground state energy? Well, it's simply, well, here I said that the domain is H2. I mean, so that this thing is in L2 when it acts on the domain. It's not important. You can also do C0 infinity. That's just fine. It will not be important for anything I really talk about, except, of course, when I talk about the eigenfunctions, then they will not be C infinity. They will have cost and so on. So they will usually be only in H2. So that's why. But when we calculate the ground state energy, you simply take the infimum of the energy expectation in this Hamiltonian of anything in here. Well, you can restrict to H2, but you could also restrict to C0 infinity. That would give you this domain. Right? And of course, the norm should be. It's really important that this energy is bounded from below. Otherwise, I'd get minus infinity, and then atoms would not be stable, and I could finish the discussion right here because we wouldn't be here. Not because the rest is uninteresting, but because we wouldn't be here. So the energy is bounded below, and I'll explain to you exactly that. Well, simply because, or let me go back, this term is positive. So when I calculate this expectation value, I get something smaller if I ignore the positive. Right? So I get that the Hamiltonian, atomic Hamiltonian, is bounded below by the easy one, where I have non-interacting electrons and no electron-electron repulsion. And this is actually a non-interacting model with this Hamiltonian for each electron, which is the hydrogen Hamiltonian. And that's exactly solvable. I know exactly what the energies, what they are. Let me just point out that there is a scaling of this, that if you scale x to z minus 1x, so if I replace x everywhere by z minus 1x, so if I replace this x by z minus 1x, then I would get a z squared up here. But the Laplacian, when I replace x by z minus 1x, I have the derivative with z minus 1x, that will also give me a z squared. So this Hamiltonian here is actually unitarily equivalent to this Hamiltonian by that scaling. So that shows that all the orbitals in hydrogen, they scale like z to the minus 1. And the energies go like z squared times the energy of this. And you see the energy in hydrogen is indeed, this is the exact formula, minus 1/2 z squared over n squared. These are the energies. There's a little mistake here when I said, well, I mean, En is, it's sort of fine to write it like this, but this is not the counting the energies because there's degeneracy. And I'll get to the degeneracy right now. But so these are exactly solvable, and this is the energy with the scaling, the Hamiltonian with the scaling z squared. One has to be a little bit careful though, because I want to fill in not just one electron, I want to fill in z electrons to get to neutrality. It's true that each orbital scales like z minus 1, but when I get to the z orbital, it's still very, very far out. So even when I scale it down to z minus 1, it still has a length that depends on z. It actually will depend on the scale. It will be much bigger. It will actually be a scale that's called z minus 1. So we'll get to that later on. So let me talk about the degeneration. So each of the levels n that I had, actually, so that's what's called the hidden symmetry of hydrogen. Hydrogen is not just the spherical symmetry because it's actually exactly solvable. So there's a much more degeneracy. Actually, hydrogen has an O4 symmetry and not just an SO3 symmetry. And so this sort of hidden symmetry tells us that there's actually added degeneracy, and each n has the levels 0 up to n minus 1 in it as degenerate level. So the total degeneracy is that you have all the levels from 0 to n minus 1, all these L's, and each of these L's, they have a degeneracy 2L plus 1 times 2. And this sum you can do explicitly is 2n squared. So each of the levels I showed you before, they have a degeneracy 2n squared, where the 2 is counting the string. So if I want to have n electrons, so I'm trying to get to, I'm trying to get to understanding what is the lower bound on the ground state energy that I'm getting from this Hamilton. And then I have to sum the energies, because when you do electrons, because of the antisymmetry, when you do the wave function, you cannot put all the electrons in the same level. You can only put as many electrons as there's room for in that level counting. It's degenerate. And otherwise, you have to sum them up. So I have to know how many I need to sum. So the question is, how many levels do I need? If I want to have n electrons, each level has degeneracy 2n squared. Well, then I have to sum n equal 1 to k to get up the 2n squared to get n. And this is some complicated third-degree polynomial in k to find out for which n, how many levels do I need to sum. We will only think about this asymptotically, and there you can see it goes like 2/3 kg. But then let me get to the lower bound. So what is the energy then? Well, the energy is the levels I have to fill. Each level had a degeneracy 2n squared and an energy 1/2 v squared over h. So that's equal to the n squared drop out. So it's actually a fairly easy formula to calculate. It's minus kz squared. That's the energy. But k was given by this complicated formula that you have to invert. But you see here that the n is actually bigger because of the 1/2 and the 1. This n is actually bigger than if I ignore the 1/2 and the. So I'm just making a lower bound by doing that and just using these. And that's a strict correct inequality that I just use the k cubed. So I get n to the 1/3 and the 3/2 to the 1/3 times n squared. So that's a lower bound on the atomic energy. Right? It's bounded below, and this formula is actually not so bad. It has the correct behavior in z squared and n squared. I'm leaving it as an exercise to give a similar upper bound. That's not an easy exercise. That's difficult. To show that when I say an similar upper bound, it means, of course, not with the same constant, but another constant and the same dependent in z squared and n to the 1. But you see here that the neutral atom goes like, and maybe I should. The human quantum is here is the constant, and that there is the n that I'm going to take into. This goes up at the lower bound I have from up there is minus 3/2. Because that's because the magic power and the heat, that's how the total energy of the system is. Let me just say one more thing. If I now count the number of levels, L levels that I have, right? Remember, K were the number of levels that these were the number of n's that I used. I'm now coming back and asking, what about this NL? Remember, that was the number of L angular momentums that I had in an atom, but only the K's that are so that it, because only L is only counted, and L here, you need an N that's big enough to have that L. Right? So when I'm asking how many, I need to start with N being L plus 1, so that if this is my L, that is actually counted in that way. Right? The L's only start appearing for large N. And then I'm counting how many of these levels, the N levels, actually have an L in it. And these from L plus 1 and up to K. That's, of course, an easy sum to do. That's K minus L. And if you now think of this formula up there, right, this was the K, right? So if the K is then related to NL by K is NL plus L, right? So this you could plug in here. You could express the N in terms of NL instead. And if I go back, you will find that that's exactly the formula I had there in hydrogen. So if I in hydrogen asked how many electrons do I have, what is the Z? I mean, this you can count from that formula there, which is exactly this formula there. Okay, but asymptotically, it's the same as I had before, 3Z over 2 1/3 minus. Okay, so now now that we know that the atom, the energy is bounded below, I can start studying. Right? I study this function. This is the total energy of an atom in atomic numbers. I want to start this as a function. And what it sounds below of this study. So I'm going to give you a drawing for what I say is the sort of like this. I mean, it's only the line of the industry. Okay, some critical values. It tells you how much you know of this thing. So this picture is still not entirely known the way I'm drawing this. But some of it is known, and some of it is not known, and if somebody can prove it, it would be really great. But what is known? So there is this thing called the Hunziker-van Winter-Schislin theorem that says that as long as it's decreasing, when n is less than n minus 1, then this n is actually an eigenvalue, and the eigenfunction is the ground state of the system. And that's just the thing here is just sort of the definition. I say is the ground state. That's not entirely correct. I should have said it is a ground state because it may not be. I mean, it will not be again. This is maybe not easy to prove, but it's fairly easy to understand, right? There's no way you can remove an electron. This would cost you energy, right? And then sort of by a variational argument, the compactness argument, you can show that there is an. I'm not taking, this is still difficult. The other theorem, Schlislin's theorem, says that the function is actually strictly decreasing for n less than or equal to. Meaning, if I combine the two, that you can bind all electrons up to Z. So what I know is that the curve there is decreasing. I drew the curve convex, and that's what we don't need. So maybe I should put that in. But we do not know here. So the maximal negative ionization, well, really what I'm interested in, the maximum number of electrons the atom can bind. If I go back up here, this is as long as it gets still negative. It could be that it's flat. I mean, if it's convex, that would not be the case, but we don't know that it could be flat for a while and then just drop again. And then you would certainly be able to maybe not bind 25, 26, 27, but bind 28. Sounds ridiculous, but we cannot prove that it couldn't be like that. But the last time where you can no longer bind anything, the term when it becomes constant, right? That's called the maximal number of electrons. That's the MQC, the thing I was trying to draw over. Yeah. At this point, I don't know that this number exists. It could be that you could bind infinitely, but I'll prove just on the next slide that this number is finite. Right? So it becomes, so that's the other part of the picture over there that I know. It's a decreasing function, and it becomes flat at some point. And one of the big questions is, what is this NC? Right? And the maximum negative ionization is NQC minus Z. It's bigger than or equal to 0, because I know by this thing that it doesn't become constant before I can get into. Good. So then I'm getting to a famous bound. So this is not the first proof that this N critical is finite. They have been earlier proved by Siegel and Wuskay. This is from the 70s. But the proof I will give you here, I'll give you the full proof, except for some technical details that you can work out yourself. Maybe not entirely trivial, but then you can read the paper. This is a proof due to Lieb that indeed n is less than, if nqcz is less than the previous one, then n is less than 2z. So there is a bound, so at some point it has to become common. Okay, so let me give you this. And the proof, not exactly the way Lieb gave it, but it's essentially the idea. So we will use the Hardy inequality in 3 dimensions. Hardy's inequality in 3 dimensions says that minus Laplacian minus a quarter x to the minus 2 is an operator that's bigger than or equal. So this thing is a positive operator. Okay, so I look at minus x Laplace minus Laplace x. So I put an absolute value x on either side of the Laplacian. And then I noticed that, well, if I try to divide half of it on both sides, so I get x to the 1/2 Laplace x to the 1/2. Well, I do it for both terms, so I get a minus 2. Then the error I'm making between these two is actually a double commutator. So it's a double commutator of the Laplacian with x1/2, and then again, Laplacian x1/2 commutator, and then again commutator. And this commutator you can just calculate. That's exactly minus 1/4 x to the minus 1, but then you split the 1/2 on both sides, and you can write this is an identity, this is equal to that. And that's greater than a. This is this is a symmetric operator, and this symmetric operator is greater than or equal to 0 on A. Okay, so now let me try to use this inequality for the quantum field. So let me calculate on the ground state, for the psi be a normalized ground state. So HZN psi is EZN psi, right? If this thing is true, then by Gislin's theorem, I do have a ground state. So there is a psi so that this is the case. Right? So I take this psi, I calculate by x, I multiply by x1/2 on psi, and I calculate the norm. And here's the first place you should interrupt me, and I didn't give you a chance to do it, because how do I know that's fine? And that's one of the places I say, okay, you have to argue why this is finite. I'm not doing this. So we'll just, these are the technical details, right? As is often the case in mathematics, there are the great, brilliant, small ideas, and then there's all the nitty-gritty work that most of us would be able to do. And that's the one I'm not doing, right? So the fact, just assuming that it's fine. Okay, then I calculate this norm and I multiply by the energy. Oh, I forgot a Q up there. I'm sorry. The Q is because I'm going to look at many different atomic models, and this is the quantum model. So I have the ground state energy EQZ of n. But the EQZ of n is the same as HZN acting on psi. So HZN acting on psi would give me this times psi, and then the x1/2 in the 2 norm would just become it. Right? So this is just that formula. Of course, I could also have let this act on the other side, right? And then I would have written it in a more symmetric way like that. But it doesn't matter because my ground state is actually real. So whether I take an expectation value with x1 on this side or x1 on the other side would give me this thing. I'm saying this because now I'm going to use this formula. I'm going to split the Hamiltonian in the part that has everything to do with electron number 1 and everything else. So everything else, well, that's an atom with n-1 electron. Right? So maybe I'll write it over here. Okay, I'm missing all the other stuff, and that's what I call and everything else, it is not have it. multiply by this one and this one, I'm going to multiply by this one. And if I use the inequalities, that's to give you a positive. If I lower down at the source, the present the idea is that when I multiply by this one there, the next one goes down again, and I get it. And here, the next one comes. That's why I wrote it like that. I have the positive terms from up here. The kinetic energy part I can ignore. I get the minus V, and then I get this term from all the repulsion. What? Where did I? Oh, the Q is missing here. Sorry, the Q is missing there. And then you have the HZn minus 1. These are all the other electrons. And here I can say, oh, this is just some function, right? X1 half psi. It's still anti-symmetric in all the other variables. So I can use it as a trial function in calculating this minimal energy. This thing here will be bigger than the quantum energy for n minus 1 electrons times the norm of this function. This is the thing, I still don't know it's finite, but it could be that it says infinite is bigger than or equal to infinite, but it doesn't, it is finite. But the point is now that I know that this EQZn minus 1, this is what I'm assuming, is strictly bigger than the EQZn. So on this side, if I replace the EQZn minus 1 by the EQZn, I just get a strict inequality. Right? And then I end up with it, then I can pull it to the other side and get the 0. And down here, what I did was, so this gives me the fact that this quantity here is less than 0. These two terms will be less than 0. This was for X1, but it's of course the same for all the other particles. So I can sum over all the other particles. So that's what I do here. I sum this term over all the particles. That will give me minus nz. And I sum this over all the particles from 1 to n. That will give me a total of n times n minus 1 terms. And I'm just counting. I rewrote them in this way. Right? So when I sum over all the particles, I would get n times n minus 1 terms. Here, I'm summing over all pairs, which is n times n minus 1 over 2 terms. But I did it twice because I wrote both xi and symmetrized it up here. So that kills the 2 again. And these two, this here is actually sum of that over all the particles, 1 and so on. This is the second great idea. The first great idea was really this inequality there. The second great idea is to use the triangle inequality. Because what's written here is greater than or equal to 1. That's the triangle inequality. So this thing here is bigger than or equal to 1/2 n times n minus 1 because psi is a normalized constant. So all in all, I'm getting the inequality that 0 is bigger than minus nz plus 1/2 n minus 1, and that's the inequality. So after that, this could not have been. Right? If n was bigger than 2z plus 1, all of this. Bigger than or equal to 2z plus 1, all of this would have been. So that's the bound that Lieb proved, and that shows that the curve is actually constant and then on time. We don't know when. So sorry, I want to finish. I have 5 minutes left, I think. So let me finish by now. They also define. So I'm now talked about the maximum negative ionization, and I gave you a first bound on it, 2z plus 1. I want to end with some conjectures on these quantities. So one conjecture here was that this curve is convex. That's not known. In fact, that was my first problem when I was a PhD student with Lieb. He told me, prove that this thing is convex. But I couldn't do it, and it's still not known. It's not even known that it's not flat at some point, that it doesn't go flat, that it goes convex, convex. So I've actually studied these things since I was a PhD student a million years ago. Okay, but let me come to the other quantities I wanted to discuss, the ionization energy and the radius of it. So let me just define a few other concepts. So there's one thing called the density the one particle density matrix. That's if you want to study one electron out of the sea of all the electrons. So you integrate out all the other electrons. So remember that each electron lives in the space of square integrable function of R3 with values in C2. I can also write this as functions of two variables, an x variable and a sigma variable, where sigma is plus or minus that spin. And I call that variable z. And when I do an integral over z, it means that I'm summing over the sigma and integrating over the x. So here I'm integrating out all the particles except the first one. And then I do psi x sigma y tau, complex conjugate, and I integrate everything else. That gives me a function of two variables, or four variables, x sigma y tau. And this actually defines a kernel of an integral operator. It's the integral kernel of an operator on this space here. And that operator has the property that its trace is n. The trace you calculate by setting x equal to y, sigma equal to tau, and integrate. So that means that you just also put these two equal to each other and integrate. So that would be the 2 norm of psi, which is 1. And then I'm multiplying by n, so I get n. What is very special is the fermionic property, and this is reflected in this one particle density matrix, that it's an operator between 0 and 1. All its eigenvalues are between 0 and 1. And its eigenfunctions are sort of the occupied orbital in the psi. That's called in chemistry the natural orbital. They can be not necessarily a 1, but they are eigenvalues between 0 and 1. That's not entirely trivial to prove, but I'll not do it here. You can find it in many textbooks, that if the psi is antisymmetric, then you integrate out, this is between 0 and 1. We will come to it a little bit later. The density is what you get here if you put x equal to y and sum over the spin. Right? And you see the trace was n, the integral of the density is n. So these are two properties I will keep using over and over again, or two sort of characteristics. The one particle density matrix gamma, which is an operator between 0 and 1, trace class operator with trace n, and the density, which is a positive, or rather non-negative function with integral n. Okay, so now that I have these, I can now define the ionization energy and the radius. Actually, the ionization energy I could have defined right away. And I want to think of the situation where I remove not only one electron, but I remove m electrons. So what does it cost to remove m electrons? Well, it's the energy if I have removed the m compared to the energy when I have not removed the m. So this is the neutral atom, and this is the atom where I have removed m electrons. This is I said here, positive quantity. That's by Zislin. Zislin said that if you remove electrons from neutrality, you would go up in M. So this is a positive number, and that's what I would call the ionization for removing M electrons. The first one is what's usually called the ionization. The radius is more complicated, but I will ask, what is the radius to these last M electrons? I can think of it as the one I removed. That's not quite how it is. But I can ask, what is the radius so that when I integrate the density outside, I get M? So how far out do I have to go so I have M electrons? So now with those three quantities, I can state the ionization conjecture. And it says that as z goes to infinity, independently of z, I will get bounds on the number of electrons I can bind. So this is at most z plus a constant. Remember, Lie proved 2z plus 1, but it should be z plus a constant, not 2z plus a constant. The radius should be bounded below, of course, by a constant depending of m. The more you remove, of course, the smaller it becomes. And the ionization energy should be bounded above by what it costs. I mean, it may cost very, very little, but it will not cost a lot to remove M electrons. So this is the ionization energy. And then there's the much more complicated question. Can I get 2 minutes? There's a much more complicated question of what actually happens with these quantities as z goes to infinity, right? I was asking about what happens as we go down the groups in the periodic table. Could it be that I have converged? Let me just finish by showing you. So I defined this RQZM, which was the radius to the last electron. And let me then go back and show you this thing, which was in that chemistry paper I wrote. So what was the red curve here? The red curve, this one I did for the alkali atoms, the ones that have one extra electron outside. So I defined mathematically the radius of an alkali to be the R1, the radius out to that last electron. And then I calculated in what's called Thomas Fermi theory, which I will get to later on. It was still a numerical calculation, and that's what gives this rate. Okay, so I'll continue this in the afternoon. Thanks a lot. No, not necessarily, because the point is that you can also ask how many extra electrons can you have to get the negative ionization. So we do ask, no, they exist. I mean, okay, that's all the question, because what does it mean to exist, right? So can you study an atom floating in the universe in the vacuum with one extra electron? That's probably pretty difficult, right? Because you have to be, right? But there are certainly atoms in batteries, right? You have atoms that are negatively ionized, right? You have the positively ionized and the negatively ionized, but then they are in some liquid, so it's very difficult to actually. I mean, so you see plenty of atoms that are ionized. Also, you mentioned salt, right? In sodium chloride, right? Then you also have that the chloride is negative, right? And no, sorry, it's the other way around, right? Yes, the chloride is negative, right? So because the electron has jumped from one atom to another one, but of course they are all in a compound or in a solid, so we don't know if there are free atoms that can bind electrons. This we experimentally do not know, but the chemists believe, from what they have studied, that you can find atoms with one negatively ionized, right? And this has, mathematically, this is also what we find, that H minus, for instance, hydrogen with two electrons is stable. But what has been seen experimentally is a little more complicated. But we do believe that there are negative ions. Mathematically, the big question is how negatively ionized can it be? If you do bosons instead, bosonic electrons, right? If you imagine you switch off the Pauli principle, then you can have hugely negative ions. Right? But this is for fermions, it's a different story. So that's one of the questions we ask. What is it? Yeah, but then you need some background to keep them together. Yes, that is. I mean, you can think of that being negative if you want, right? But of course, they're not stable. In fact, I think I made a mistake here. If you go to how did this happen? You see, in my definition, it was not really a mistake, but maybe a little bit silly. When I defined this maximum number of electrons, I said n in z, in z. I mean that the n could also be a negative number of electrons. That's not wrong, right? Because it just doesn't make any sense to think of it. But you can think of z being negative. N, of course, is always greater than or equal to. Yeah. Oops. Yeah. No, it's not even a metal. No, because this is all, it's not even a metal, because in R3, this is all in R3. So if you have only the kinetic energy and the repulsion, they will just fly apart, right? So the atom disappears. And that's actually why this is actually the correct picture. The energy in that case is zero. The ground state energy is zero. It's not a ground state. It's just but you can get the zero energy in that case by just putting the electron very far away. But it's a meaningful thing, and you could also take the negative, and you would find the same thing, because then even the nucleus would repel the electron. Yeah.